So now the goal is to convert back and forth between rectangular coordinates and polar coordinates. So in this example, I've given you a couple of sets of rectangular coordinates, and the task is to convert it to the polar form. So first, just to review the conversion equations that we have available to us. If you ever forget, just draw yourself a little picture in quadrant 1. So let's say here's a point in quadrant 1. Let's say the polar coordinates are r, theta. That means that if there's this ray extending out, pretend that's a line. That's pretty bad. Extending out from the origin through that point. So this ray would correspond to theta degrees, or, well, radians, either way. Let's say theta radians. R is the distance out from the origin. So R would be the length of this line segment right here. And let's say that the rectangular coordinates for that point are x, y. So x is the distance out from the y-axis. This distance right here would be x. And then this distance right here would be y. And this would form a right angle right here. So we've got a right triangle. Now, so a couple of things we can note here. First of all, it's a right triangle, so Pythagorean theorem applies here. So x squared plus y squared must equal the hypotenuse squared, which is r squared. So there's one useful equation. Also, we could use the old SOHCAHTOA definition of the trig functions. So notably here, tangent of theta would be opposite over adjacent. So tangent of theta is equal to y over x. Okay, we could also say, well, then cosine theta is adjacent over hypotenuse, so that'd be x over r. That gives us the equation, if we multiply both sides by r, x equals r cosine theta. Similarly, sine theta is equal to opposite over hypotenuse, so that'll be y over r. If you multiply both sides of that equation by r, we have y equals r sine theta. And so these are the important conversion equations. So the x equals r cosine theta, y equals r sine theta, and these equations up here are going to be the useful ones when we're converting back and forth between polar and rectangular coordinates. I'm going to get rid of this diagram in the middle here, since we're not necessarily talking about points that lie in quadrant 1. Okay, but here's the critical information that's in those boxes. Okay, so now looking specifically at this example. So the point negative 2, 0. It is helpful to draw yourself a quick diagram to actually plot this point. So negative 2, 0, the x-coordinate is negative 2, the y-coordinate is 0. So that corresponds to this point right here. So if we want polar coordinates for that point, one way to write polar coordinates would be, okay, this ray right here corresponds to pi radians, and we move positive 2 units out along that ray. So 2 pi would be one set of polar coordinates corresponding to that point. Something else we could do is use 0 as our theta. That would correspond to this ray right here, and then move negative 2 units along that ray. So negative 2, 0. This now, notice, it's the same coordinates that we had in the rectangular form here, but so this is x, this is y. In the rectangular form, this is r, this is theta. Turns out in this case, it happens to work. Those coordinates happen to work as both polar and rectangular coordinates. Either way, it does correspond to this point right here. Okay, so there's that one. This one maybe will be a little trickier. It's definitely trickier to plot, but I'm still going to draw a quick picture. It's just nice to have a reference to at least know what quadrant we're talking about here. So negative square root of 3. So that would be between 1 and 2, right? Because the square root of 1 is 1, the square root of 4 is 2. So we're between 1 and 4 here in the radicand. So this will be between negative 1 and negative 2. and then, so let's say negative square root of 3 somewhere in here, and then positive 3 for your y coordinate. So we're talking about point in quadrant 2 for that negative square root of 3 square root of 3 coordinates. Okay, so we want some polar coordinates. So let's think about what would this ray right here be? What's the value of theta, or what is a value of theta corresponding to that ray? So the way to find theta is to use this equation here. The way to find r, by the way, while we're talking about, is to use this equation here. But so we're going to depend on these two equations when you're going from rectangular coordinates to polar coordinates. If we were going the other way, if we were given r and theta and we wanted to find x and y, that's actually really straightforward, and you just use these two equations here. Going from rectangular coordinates to polar coordinates is a little bit touchier, just because the way you see that we have infinitely many sets of polar coordinates corresponding to a single xy pair. So you can just tell things are going to be a little more complicated just based on that fact. Okay, anyway, so let's use the equations. X squared plus y squared equals r squared. Let's do that one first. I guess that's the most straightforward. So x is negative square root of 3. Y is 3. So this is, when you square it, positive 3 plus 9. So 12 equals r squared. So r may be plus or minus the square root of 12. Which it's nice to simplify that. So the square root of 12, oops. So let's say it's plus or minus, 12 is 4 times 3. We want to find any perfect squares that are factors of 12 and go ahead and take the square root of that. So that's plus or minus 2 square root of 3. And we want to keep the plus and the minus there because you see from over here, you can write your polar coordinates with either a positive or a negative value of r. We usually prefer to use a positive value of r, it just keeps things simpler. But you could use negative 2 square root of 3 as well. Okay, so this is what we have for r. It's based on that x squared plus y squared equals r squared equation. Let me get rid of the work here so I have some space. And I don't think we're going to use these. We're not going to use those equations either. Okay, this equation now. So tangent of theta equals y over x. I don't like to write this, so I don't like to write theta equals arctan of y over x as a conversion equation. Because if you remember, arctangent has a specific range, and it's negative pi over 2 to pi over 2. I don't want to be stuck using only thetas between negative pi over 2 and pi over 2. So that's just like the right side of the plane here. I want to be able to use any value I want for theta. So that's why I like to keep it as this equation, tangent of theta equals y over x, as opposed to theta equals arctangent of y over x, because I don't want to limit what I can use for theta. Okay, so we want to solve this. We know we want a solution in quadrant 2. It may help to rationalize the denominator with things like this. If it's looking like something that you might see on the unit circle, but it doesn't immediately look recognizable, you could try multiplying numerator and denominator by square root of 3. So that'll rationalize the denominator on this thing. And so you'll have negative 3 square root of 3. I'm just moving the negative out front. And then square root of 3 times itself, so that's 3, so these cancel. So we want a value of theta in quadrant 2 where the output of the tangent function is negative square root of 3. So if you have a unit circle handy, look at the ratio, y over x. When is the ratio y over x equal to negative square root of 3 in quadrant 2? So that's going to be when the y is square root of 3 over 2, the x is negative 1/2. So look for these coordinates in quadrant 2 on the unit circle. That's going to occur at 2 pi over 3 radians. So one possibility, 2 pi over 3, set of polar coordinates here would be positive 2 square root of 3. Theta is 2 pi over 3. That's one way we could do it. We could also use a negative value of theta if we want, or I might even, so this ray right here would correspond to negative pi over 3 radians. So what if I use negative pi over 3 as my theta, and then negative, I'd have to use a negative r also to move backwards into quadrant 2. So negative 2 square root of 3 as my r. That would work as well. But this is the simplest response. There's a set of polar coordinates corresponding to the rectangular coordinates negative square root of 3, 3.